Hello everyone. Today we're going to be talking about tokenization. And if I was to do this in person, I would hand out this short 2-page paper to you, but it's available to you in Learn. So by the end of the lecture, you'll probably want to go and pull that up and be able to refer to it as appropriate. In reading, catch you up. Again, largely you can figure out what it is to read in the course based upon what I'm talking about in the course textbook. Again, I'm going to primarily often refer to the search engines, Information Retrieval and Practice by Croft, Metzler, and Stroman. And I might refer to the other textbook at times, but at the moment, most of the references will be out of here. But I really want to encourage you to be able to dig into both of these, all right? Be looking for the material. This is sort of the bare minimum to read. So this is, you have to read this stuff, to really be following along and to fill in any gaps that might be in the lecture. But the real idea of a course like this is to try to absorb as much as you can. Hopefully you find it interesting and you want to learn more. And there is just so much more to learn. And so yeah, it's basically, this is not all of chapter 4. You could read on, all right? Same thing with chapter 5. And then, yeah, same thing with chapter 5, I guess. And so basically, in chapter 5, you're reading the first part of the chapter, and then here, just these subparts of subsections of section 5.3, and then section 5.5, and again, just these two subsections of 5.6. And this is largely going to cover the material that I'm going to talk about with regard to tokenization. And then this is going to move you into the next topics, which are dealing with term statistics and then indexing. All right. So yeah, our next topics will be things like term statistics and indexing. All right. So let's dive into tokenization today. And yeah, so I will tell you what to read in lecture. So that's where the announcements of what reading material is. Okay, the tokenizer. So it's the software that we're going to use, the algorithm that we're going to use, whose goal is to break a document into tokens, which just is basically saying a bunch of strings, because a document, as we know, it's one long string, a whole bunch of characters, letters, numbers, punctuation, spaces, all sorts of stuff. It's just one long string. To us, we see it because we've learned how to read. We break it up into words that all has meaning to us and so forth. To a computer, it's just a string of characters. So it needs we need to give it an algorithm to basically break it up into tokens, which are also called variously as we go through the course. You'll see at times referring to them as terms or words. Tokens are perhaps the most appropriate thing to call them, because we could have something where like, that's not a word, but it is something that we've broken the text up into and stored, and we're using to associate that string with a document. It's one of the many strings. Okay. All right. So token is perhaps best so that you don't fall into the illusion that we always have perfect terms or words associated with these documents. We won't. we're going to have these strings that we've computed and associated with these documents. All right. Now, most of the time they will look like words, so that's good, but they aren't always perfect words. So we certainly shouldn't think of them that way. One thing I want to note right now up in front so that no one thinks otherwise is our tokenizer is going to be, so we'll apply it to a document to break it up into words. We are also going to apply it to whatever our user's query is. And so we're going to be having users put in natural language text. We're not going to be supporting any fancy query languages or anything. We're just going to say put in some text. And so we're going to kind of end up in, for our search engines, we're going to be treating the query that someone puts in as like a really short little document. And we're going to apply our tokenizer to that and produce a bunch of tokens. We will then take those tokens and the tokens in a document and applying an algorithm that we could call a similarity algorithm. It measures effectively a score, which is like the similarity between the little document that the person supplied as their query and the document that we have stored in our index. Then we're basically able to compute that for all the documents in an efficient manner, and the documents that are most similar to the query are the ones that we're going to show the user first in the ranking. Now, it's not just always a notion of a similarity. The ranking measures go beyond just notions of, oh, this is similar. So it's not simple matching. But for us to do things, we will be matching the tokens from the query with the tokens that we have in the documents and counting various statistics and things like that. And so it is very important that we apply the same scheme to the user's query. And the idea here is so that the tokens match those in the document. All right. One of the things that we're going to have, we're going to see when our basic tokenization scheme is that we're going to downcase or lowercase, use lowercase, for example, lowercase the terms, the tokens. So if we downcase all the tokens in a document, but don't downcase a query, there's no way. So let's say someone, as part of their query, they put in all capitals USA. So there's no way USA could match anything and could match any document. Now this might seem a little premature to be talking about what to do with the user's query, but I want to get this idea in your heads now that whatever scheme we apply to documents, we apply that same scheme to the queries. This is one of the biggest mistakes students make in building search engines is they think, oh, I'll do something different for the query. And then they don't understand why the quality of their search engine is horrendous. Well, it's because they have, like, we talked about vocabulary mismatch in a previous lecture. So again, vocabulary mismatch is where I come up with index words to describe something, you come up with index words to describe something. We're unlikely to be using the same words. So we'll have a mismatch in our vocabulary. This is the way humans are. If you do something like this is like an algorithmic mismatch, vocabulary mismatch. It's like, I programmed the computer so that they wouldn't match. I mean, you wouldn't do it on purpose. It's entirely a mistake. But for some reason, it's not obvious to a lot of people that this would be the wrong, that they have to do this. They'll do something different and they think it might improve things. It will not. You want to do the same thing. All right. Or if you're not going to do the same thing, it's something deeply intelligent with regard to your knowledge about how the tokens are created in the documents. But in general, the thing to do is apply the exact same tokenization scheme to the queries as to the documents. All right. So in this course, we are going to use a very simple tokenization scheme. And this is the basic outline of the scheme. As I mentioned, the first thing that we're going to do is downcase the text. Okay, and so what this means is to convert all letters to lowercase. Now I will mention, so if we had Mark, it becomes all lowercase. All right. So I'll mention though, if it's not clear, everything here is being taught with regards to English retrieval. I actually don't know for the languages that don't use similar characters. Do they have capitals, uppercase and lowercase? I don't know. I don't do foreign languages for retrieval. Certainly, researchers around the world do work on other languages other than English. I think one of the things that's going to be important to note before I go through this small example is the concepts that we talk about are absolutely end up to be the same. So whatever the language is, for the retrieval methods that are in use, you still have to find a way to break it up into some tokens, into some units of meaning, things that mean something. Okay, so you got to chop up that long string of the document or whatever it is into pieces, usually. Okay. That's usually the case, that we've got some linear thing and we need to chop it up into pieces. And then we're going to do various other things to those pieces, some other transformations and stuff, and then we're going to end up with a final result. That final result is then what we're going to index and use in our ranking algorithms. And people do this in all sorts of languages, and the same concepts are at play, but the details are, of course, different because the languages are different. Anyway, so we could have a name, such as mine. We capitalize names, proper nouns, and to downcase it, we convert all of it to lowercase. These are already lowercase, so it's just the first letter that changes. What sort of advantages why would we be doing this? So advantages to downcasing, a great thing is the user does not need to be careful. With case in their query. And you can certainly think about, a lot of times you're like, do I really need to be bothered with hitting the shift key? I just want to tap in a word and hit search. Like, does it really matter? Imagine if you always had to think carefully about it and to think, ooh, let me get the capitalization right for exactly what it is that I'm looking for. So that's a nice, it's a small thing, but it's handy. But perhaps one of the other nice things is in English, all of our sentences start with a capital letter. So this allows us to match words at the start of a sentence. So we might put in a word with lowercase as a user, because why would we a lot of the words we're going to use are not proper nouns. Why would we capitalize them? But a lot of those words could very well be the subject of a sentence. As a subject of a sentence, it might very well be the first word. And as the first word of a sentence, we're going to capitalize it in our documents, unless we're E. Cummings and doing poetry or something. So we don't want to, if we don't do that, all of those capitals in words capitalized at the beginning of sentences form a different set of words from all their lowercase usages throughout the document. So when we decide we're going to end up counting how many times we see a word in a document, we'll have a count for the word with its capitalization and a count for the word with it lowercase. The user puts in a query, they might do lowercase, and we're only going to be counting the number of times the lowercase word is. Those are the matches we're going to find. We're not going to find any of the capitalized matches. That seems really weird. That doesn't seem like a good idea. So that's probably one of the biggest things, all right, is in English we start sentences with capital letters, and this is a way to fix and deal with that issue. You could envision other solutions to the problem, but this is a really easy solution. What sort of a disadvantage might this have? Well, this is going to lose the ability to discriminate or distinguish certain acronyms and proper nouns. So you might very well, though, we talk about the easier for the user and stuff. But what if you were looking for a town where I spent a lot of time as a child, Pleasant Valley. So I didn't live in Pleasant Valley, but I had a high school in it. So Pleasant Valley, this is in Iowa. There's probably lots of Pleasant Valleys. But boy, Pleasant Valley as a proper noun is quite different than you might find in text. People talking about things being pleasant, and they might talk about valleys. Oh, wait a minute. If I query with capital letters, because as a user, I know I want the town, I'm looking for things about Pleasant Valley, this could really be a helpful hint to the search engine, because it will only get positive matches with index terms on documents if we had kept the capitalization. Okay, so it's like, if we had kept the capitalization, we would be able to notice and recognize that this document is referring to Pleasant Valley as a proper noun. So we could hone in on and help you find what you're looking for. When we gain the advantages of downcasing, for a query like this, we hurt the user, because now we're going to match the words pleasant and valley all throughout the collection, and not just only when they're capitalized, which is a hint that they're being used as proper nouns, rather than just at the start of sentences. So this is, again, this whole trade-off between precision and recall. So downcasing is a recall enhancing technique. It's going to allow us to obtain many more matches for the same query. And so we're much more likely to bring back as potential candidates that we might find as relevant as a user if we've downcase. But at the same time, we're bringing in all this stuff. That also means that there's a good chance that we've brought in a lot of stuff that's not relevant to us. So we're going to be, in effect, lowering the precision of our results to the user. So it's really hard to increase our recall which is the fraction of things, fraction of finding all the relevant items. So it's hard to maximize that without also then decreasing the precision, which is of the things that we show the user, what fraction of them does the user actually find are relevant. All right, so the next thing that we're going to do after we downcase it in our tokenizer is, and this is the last step basically, is we're going to break the string, break the text, break the document up on non-alphanumerics. So wherever we assign something that's not an alphanumeric character, we're going to say chop that string. Okay, so what are the alphas? Well, the alphas are A through Z, or Z for those, and the numerics are 0 through 9. So those characters. So if we don't see a letter or a number, those are places where we should break the string up, okay? And sections that are contiguous alphanumerics we'll keep together as tokens, and everything else will turn into the stuff in between our tokens, which we don't care about. And so we're only going to keep sequences of alphanumerics. All right, so let's take an example here really quickly. This example comes from a piece of text in this short paper, the tokenization paper. So this is why it's basically, I'm going to put it in quotes because this is not my language. They write, we use 2 IR models in our experiments, one, actually, since I'm quoting them, I should be sure I do it right. 1, probabilistic language modeling. And then it goes on. Okay, so this is just a small example. So if we're going to do this, we're going to downcase it and we're going to break on things which are not alphanumerics. So our tokens that we're going to produce are just really easily, we're going to go, we use 2 IR models in our experiments. 1, probabilistic language modeling LM. So these parentheses are thrown away. That parentheses thrown away. This semicolon is gotten rid of. Everything is in lowercase. These spaces are not a letter and not a number, and so we throw them away too. All right, that's a quick example of how the tokenizer is going to basically work for us. We will also in the class, and we'll talk about it later today, we'll talk about using a stemmer and removal of stopwords. But first, let's look at a simple algorithm to do this. Okay, so this is, you could call it pseudocode, but it is almost entirely Java. But since it's not perfect Java, it's not really Java, we'll call it pseudocode. This is based on Code by Trevor Stroman, one of the co-authors of the textbook. And this is from the Galago search engine that was designed to go with the textbook. We don't ever use that search engine, but we will yank out of it basically one of the simple tokenizers it had inside of it. So let's downcase our text. So this is pretty easy. All sort of languages nowadays have some method to take a string, make it lowercase. Okay. We'll make tokens be an empty list. So this could be, it's like a vector, an array, something that we can utilize, and we can add tokens to collect them as we find them. Say start is 0, and then for I is 0, I is less than the length of the text. We'll increment I. And we're going to have this variable C that stores the character at the ith position of the text. And then if C, this is the great pseudocode part, is not a letter or a digit, and then if start does not equal I, I'm doing race styles in a way to save space on this little whiteboard. We'll get a token out of this by taking a substring from the text. It goes from our starting position to I minus start. Okay. This is just computing a number of characters. So this is we take a substring out of this piece of text from this position forward this many characters. And we take that, we grab it, make a copy of it, and we're going to store that string in our token variable. And then we'll just go ahead and add that token to our tokens. All right. Then we've got that. And then we're going to this place, we advance start to one past where I is. Down that if, down on that for. And then if we've got to clean up here, you have to repeat this. If start does not equal I, then we're going to do there's one last token actually that we need to grab. That's it, because we'll hit the end of the string. And so if we hit the end of the string and there's still something there based upon where the start is, so if the start is not at the end, then, oh, there actually was a token at the very end of the string and we need to grab that token. So it's again the same notion where we get a substring from start for this many characters. And at the very end of all of this, we return the tokens. All right. So again, let's walk through this real quickly. Take our text, we're going to lowercase it. We're going to make a list to store in the tokens as we find them. We have this notion of these two indexes that we'll keep, start and I. All right, so let's say that we've got a piece of text which is after it's been downcased, it says MSCI 541. Okay, the idea here is that start comes in and is basically at index 0, is pointing there. And then we have I, and I also ends up there, okay? And then what we do is we go and we say, all right, we're going to go into this loop, and we're going to check to see what's at the I position, when I is currently pointing at the start of this string. So if C is not a letter, nor is it a digit, well, it happens to be. So we're down there, we're going to loop back. And so the action there is, oh, while we're seeing letters or numbers, the idea is we're going to be advancing I. So then I moves ahead and looks at the S. All right, it comes in here. Ah, yeah, it's a letter. Well, okay, well, advance I again. And I starts to looks at the C. Yeah, that's a letter. All right, advance the I. We're not doing anything with the start yet. Advance it. It's going to be referring to the I. It's still a letter. All right. And then we're going to advance it, and it's going to be looking at this space in here. To be clear, we can, when we write strings, we can make a space with this sort of notion there. So now I happens to be looking at this space. So C, yeah, it's not a letter. Okay. Is start set equal to I? The answer is no, it's not. So that means that we started with I and started in the same spot, but then I moved ahead as it went over letters or digits, and then it eventually found something that's not a letter or digit. So now we've captured that we've got a string that we want as a token. So we grab that off, and our first token is MSCI. Wish I could spell my simple acronym. Gosh, too hot in this room. All right, MSCI. It becomes the first token that's added to the set of tokens. Great. Anyways, we've done that. And then what happens? Well, now we're here. And so this shifts start to 1 before I. So start ends up looking at 5. Then we come and do the for loop, and I moves up to the 5. All right, and hey, yeah. Okay, well, again, we got the same behavior here, which is race I on down until it hits something that's not. Again, we'll discover, we found the next token. We'll save that, and then we'll move start up again. If I had multiple spaces here, what would happen is we would end up moving both I and start along until we hit our first letter or number, and then I would move until we hit the end of that token. So this is a really nice, simple tokenization scheme. The algorithm is quite simple to code. We pass in our piece of text that we've gotten from our document, and it'll return us a set of tokens. If you want to save a little bit, make it a little bit more efficient, instead of creating the empty list in here, you could reuse a list over and over, but then you have to remember to empty it back out after you've finished dealing with the tokens there, which is something some students have problems remembering doing. So if you do it this way, you'll be sure that you always have reset the tokens list. But the problem with this is this requires a new allocation for every single document, because this will be a piece of text from a document that you're going to process and tokenize. And so that adds overhead to keep allocating the list and then freeing it, allocating the list and freeing it. Instead, it's better to just allocate it once, be sure it has nothing in it, send it into tokenize and use it, and then it will be filled with the tokens. Use them in your indexing and other processes, and then reset it. It won't free up the memory, but it also won't have to allocate more memory, and then you can just reuse it and send it into tokenize again. It's not a hard idea. It's a small optimization. I hate to talk about those things because then people focus on them, but I did want to mention that we try, if we can avoid allocating and deallocating over and over and over again, usually that's a good idea. But it's a really minor thing for the efficiency. It's not, in other words, this is the type of thing that in your algorithms and data structures courses, when we talk about the constant factor, that's exactly what that is. That sort of optimization just changes the constant factor. It makes it run a little bit faster. Doesn't change the algorithmic complexity at all. I mean, that's a nice linear algorithm. Okay, so there's nothing that would change that. All right.